Welcome back. So what we're looking at right now is verbal models and basic graphing of inequalities that you might have when you've got, x is greater than 3, x is less than 3, or a compound inequality. I'm going to do two of these examples for you, and you can fill in the rest. The first one that we're going to look at here is this inequality that reads x is less than 3. And so when we look at a verbal translation, there's a lot of ways you could say it. I literally just read it. But what I'm more looking for is how would we describe this interval? So we'd say something like this: all numbers less than 3. Okay, so all the numbers less than 3. So x could be anything, so it's all numbers less than 3. When we're doing the graphs, we're going to do this in a very specific way. There's a couple of different ways to do this, but our goal for this section is to talk more about interval notation. And so when we draw our graphs, we want to draw them kind of as an interval, and you're going to see that there are some upsides and some downsides, but it's really pretty straightforward. In this case, what we're doing is, for the graph, I'm going to give my featured number here is going to be 3, and if I want all the numbers that are less than that, I'm going to put an arrow going this way. Now you notice right here, I used a parentheses for less than or greater than, and I'm going to use a bracket for less than or equal to, greater than or equal to. Okay, so that's going to be our notation and our diagram model that we're going to use in this section. So when I jump down here to this third one, so this one, everything I leave from these set of boxes is going to be for you. In this third line here, I've given you the verbal translation. So the real number is between -4 and 0.5. And so let's fill in the inequality first. Actually, it might help you to do the graph first, but we'll do the inequality first. So if it's between -4 and 0.5, what goes in the middle here? This is what we call a compound inequality. And so -4 is less than our number, which is less than 0.5. Okay, and so when we go to draw our graph here, we're going to have two featured numbers. We'll have a -4, and we'll have a 0.5 here. We're going to give them each a little stem on our number line here. And because they are both less than signs and they don't have any equal to, we'll have something that looks a lot like this. So it's the real numbers between -4 and 0.5. Okay, and so as you go through to fill in these boxes, what I would like for you to do is this. We did an example of this one, compound inequality, describe it, graph it. For this one, work backwards from the verbal translation to do the inequality and also the graph. Down here in the gray boxes, what you're going to do is you are going to write a one-sided inequality. This is a one-sided inequality. In here, you're going to write a compound inequality, and you're going to fill out the boxes. So you are creating the problem and filling in the 3 boxes for it. You can't use the one that I used, though. Okay? Thanks for watching, guys. We'll see you next time. Welcome back. For this section, what we're going to be doing is we're going to be talking about specific intervals and how do we describe them, describing and graphing. So I've got a bunch of boxes here, and I'm going to show you exactly what I want you to do in them. I'm going to do the top row of boxes, but first I want to give you a little bit of background information. When we talk about intervals, they're either bounded or unbounded. And so the basics of bounded versus unbounded look like this. If you think about the concepts of bounded and unbounded, it makes me kind of think of like boundaries, okay? Bounded intervals are going to have numbers on both ends. Okay, so something like this, numbers on both ends, numbers on both ends. These are not numbers on both ends. So it kind of begs the question, well, what would it look like not to have numbers on both ends? And so an unbounded interval has infinity or negative infinity in it. Okay, and so from there we can talk about these intervals a little bit more informedly. So first of all, we're going to do this first row of boxes. I'm just going to go through. I'm going to label them either bounded or unbounded. So here we go. This is a bounded interval. Okay, it's bounded because it has numbers on both ends. Again, bounded. Okay, these two are unbounded. And this one's also unbounded. Okay, and so as we go through this, there's another label that we need to put on it. It is a bounded interval can be open, closed, or half open. Almost wanted to say half there, not a word. Okay, so for example, this one, to be open is to have that parentheses look, okay? It doesn't include the number. To be closed would be to include the number. So my open ones have parentheses. My closed ones have brackets. My half open one has one of each. So this one would be half open. Okay, this one's half open because it has half that's open, the other half is closed. This one would just be open because it has two openings. Okay, a bounded interval can either be open or closed. It can't be half open because as it goes to infinity, we're not considering that point. So it's either open or closed. This one is open, and this one is closed. Okay? Open, closed for unbounded, half open, open, or closed for bounded. Okay? What are you going to do for yours? In the next 8 boxes, what you're going to do is you're going to label and draw. Okay? So for example, in this one, this is closed and bounded. Right? Closed and bounded because it has numbers on both ends, so it's bounded. It's closed because it has these brackets here. And so then I'm going to sketch it, so I'm going to go between -3 and 5. There's a couple of different ways to do these sketches, but for the purposes of this section, we're going to be using the sketch that includes our endpoints as either parentheses, meaning open, or brackets, meaning closed. Okay? You're going to do the same thing I just did here for these 3 boxes. Then down here, you are going to create the number part. So I've given you that I want an unbounded closed interval. So I'd like for you to create that unbounded closed interval. And if it's possible, write one and sketch it. And that's what's going to go in your box. So you're going to write an interval and sketch it if it's possible. If it's not possible, you say not possible. Okay? That's what you're going to do for the next 7 boxes. Thanks for watching, guys. We'll see you next time. All right, welcome back. In this station, we're going to be exploring how the inequality, the interval, and the graph all work together. So for example, in this first one, I'm going to do 2 examples for you. Actually, in this section, I'm only going to do 1 example for you because I think you're going to catch on pretty quickly. For this one, I'm matching inequality, interval, and graph. So given the inequality, -6 is less than or equal to x is less than 3, my interval is going to look like this. My bracket tells me that it is possibility of being equal to. My not equal to, my parentheses tells me not equal to. Okay, so if it's got the line underneath it, it's going to be squared off. If it doesn't have a line underneath it, it's going to be parentheses. And so in this case, I'm going to label my -6, give myself a stem. I'm going to label my 3, give myself a stem. And I'm going to go this way. Boom and boom. Make sure you clearly make those either squared off or rounded. That's all there is to it, guys. When you get down to these bottom ones, you're going to create a double-sided inequality. And here you're going to have one that's open to infinity. So you're going to have infinity on one end. And that means you're going to have a parentheses because you can't box in infinity. Okay? Thanks for watching, guys. We'll see you next time. Welcome back. In this station, we're going to be looking at using the properties of exponents to simplify expressions. You're very familiar with these, but it might take a little bit of brushing off the dust to try to get yourself into the swing of remembering exactly what's going on. I'm going to do the top 3 examples. I'm going to leave the bottom 3 for you. The key to doing exponents is to remember that when you're multiplying, because essentially this is all just multiplying, the commutative property says we can move all of these elements around and put kind of like the terms that go together. So for example, this is 2 times a times b cubed. And then times 5 times a squared times b to the 5th. And so if I move these elements around and put the numbers together, 2 times 5, and the a parts together, a times a squared, and the b parts together, b cubed times b to the 5th, I could then easily simplify to give myself 10 a cubed b to the 8th. That's my answer. That's using the commutative property to move those elements around. In the next one, we actually have a couple of things going on. We have a division problem here, and so we're going to be reducing exponents potentially, but really my more pressing concern is to eliminate these negative exponents. What we need to remember with negative exponents is they switch and become positive. So negative exponents switch and become positive. What do I mean by that? I'm going to rewrite this problem. U squared times v to the negative 2 over u to the negative 1 v cubed. Here's what happens. This exponent is negative. It goes to the bottom and becomes v squared. This u to the negative 1 goes to the top. It switches and becomes u to the first. So what does that mean? Let's simplify. On top, u squared stays. And now on top, this u to the first, so this u to the negative 1, went up top and became u to the first. And here I've got v to the negative 2 going to the bottom and becoming v squared. And I still have v to the third power. When I simplify, I've got u cubed over v to the 5th. So I have negative exponents eliminated, which is one of the properties of simplification. I have to rewrite with no negative exponents. So to get rid of those negative exponents, they simply switch and become positive. In letter C, I don't have any negative exponents, but I've got this big negative exponent out here. When I have exponent outside parentheses, it actually gets distributed to the top and the bottom. And so what happens is this is x squared times negative 3. I'm multiplying my exponents. When it's outside the big parentheses, I multiply the exponents. So this is 2 to the first times negative 3. If I simplify that, I have x to the negative 6th and 2 to the negative 3rd. Well, what you notice now is in simplifying, I've now made it where I have negative exponents. And so 2 to the negative 3rd goes up top and becomes 2 to the 3rd. X to the negative 6th goes to the bottom and becomes x to the 6th. So I could rewrite this as 2 to the 3rd, which is 8, over x to the 6th. How else could you do this? Well, you could just flip it over right away, and flip it over right away to eliminate that negative 3, and then distribute the distribute the third, the power of 3 to both exponents right away. But this is essentially what the elements mean when I multiply it in and then switch them around. Okay? Thanks for watching, guys. We'll see you next time.